reduction of the order method. Reduction of order method. One often needs to find another linear independent solution. We will use reduction of order method. So one often needs to obtain a second linear independent solution where one solution is already known. Is already known. Okay. So to develop this method, we will show our previous case where y double prime plus ay prime plus by equals 0. We have already obtained. So when the a squared minus 4b is equals to 0, we only can get one single root where the y1 is equals to e to the minus a over 2. So this is our single root. And we are trying to use the reduction of the order method to have the second linear independent solution. So how this reduction of order works, we have like 2. We assume the second linear independent solution look like ux times y1 x, where the y1 x is already known here, okay? So this is to be determined. y1 x is already known, okay? And when you have these equations where y double prime plus py, not p, so in the case will be ay plus by equals to 0, uy2 is equals to uy1. We know that where the u is as function of x, y1 is as function of x, okay? So our y2 prime will be equals to u prime y1 plus u y1 plus prime. We also know y2 double prime will be equals to u double prime y1 plus u prime y1 prime plus u prime y1 prime plus u y1 double prime, okay? And you can rewrite this as u double prime y1 plus 2u prime y1 prime plus u y1 double prime, okay? And you can put these equations y2 double prime, y2 prime, y2 back into your original solutions. We substitute y2 double prime, y2 prime, y2 back into the second order ODE, okay? Then what we can get from our initial y double prime plus ay plus b equals to 0, we can get u double prime y1 plus u prime 2y1 prime plus a y1 plus u y1 double prime plus a y1 prime plus b y1 equals to 0. So you can try to substitute by yourself. This is after arrangement, after we put all the u double prime, u prime, u together with the coefficient. We can say this is kind of like a coefficient there. That is arranged formula is equals to 0. And you know that y1 double prime plus ay1 prime, here is ay1 prime, plus by1 is equals to 0. So this part is equals to 0. And what we have left, which is u double prime y1 plus u prime 2y1 prime plus ay1, that is equals to 0. Okay, because this is exactly the second order there, so that part is 0. And what we can do next, we are trying to change the second order of the u to be a first order of the other function. We can use z function, another representative function, to lower the order of this second order of u. So what we do is, let's assume that u double prime is equals to z prime, u prime equals to z. So we substitute u prime with z function, and z just first order will be equals to the second order of the u double prime. Then what we can write is z prime y1 plus z 2y1 prime plus ay1, that is equals to 0. And you can see that this is actually a separable equations where you can separate the z part on the left, you can output the y part on the right. So we can use separable form to solve this first order ODEs of z direction, okay? So we can get, okay, the z prime divided by z is equals to negative 2y1 prime divided by y1 plus a, okay? So that is after putting all the z part on the left, y part on the right, we can get this equation. Then we can just integral both sides to get our final solution, right? So we can integral both sides to get our final solutions. Where we can get is ln z, that is equals to, okay, ln z is equals to negative 2 ln y1 plus the integral of a dx here, okay? We can also put all the ln part on the left and leave this part on the right. So the ln z y1 squared, that is equals to ax, okay? Then you can get, okay, what is the z? The z will be equals to e to the ax divided by y1 squared. Okay, that is u z direction. And what is u, sorry, this is negative ax, so negative here. So what is u y1? Y1 is from our original solutions, that one solution is e to the negative a over 2. So y1 squared is e to the negative ax. Then the z will be equals to 1, right? And what is uz before substitution? Z substitutes u prime. So you can integral both sides. Then to integral both sides of x, then you can get what is your u function. So it's integral both sides will be x equals to u. And this u is as function of x, right? So ux equals to x. Then what is your second solution? You know your second solution y2x by assuming substitution ux y1 x. So u y1 is e to the negative a over 2x. So there is an x here, sorry. Ux will be equals to x. Then your second independent solution will be x times uy1. And what is your general solution after solving this? It's a linear combination of two solutions, right? So that will be yhx is equals to c1y1 plus c2y2, which is c1 times e to the minus a over 2x, c2 by 2 will be x times e to the negative a over 2x. So this is your general solutions. And we have to put a note here after solving such constant homogeneous solutions. We found that if you only have one single root, multiply by some power of x is quite useful for linear constant coefficient equation with repeated root. Okay, so this is a perfect example showing that your homogeneous equations is a second order linear ODE with constant coefficients, and you only have repeated root, meaning just one root after solving the characteristic polynomial. Then you just times some power of x. Here we solve that it's only x there. It will be quite useful for guessing what is the second linear independent solution. Okay.